So good morning, everyone. Thank you, Mrs. Chairwoman, for the presentation. I want to first thank the organizers for organizing this conference and all of you for attending it after this very difficult year for all of us. So I would like to present this work titled 2D maps of electronic density and temperature by spectrotomography diagnostic in a linear magnetized plasma. This work has been done in the BIM laboratory at the Aix-Marseille Université and the CNRS. So here's the outline I will follow during the presentation. I will start with a very short introduction. Then I will explain experimental arrangement. After, I will give the theoretical frame from this work, the coronal model of plasmas. And after, I will explain the method and the measurements for the electronic temperature and the density determination. And finally, I will arrive to the conclusions. So everyone here is aware that plasmas are present in such a wide range of applications in research and in industry. But to have a good performance of this plasma is fundamental to know this kind of plasmas. For example, via important parameters as the electronic temperature and density. So in this challenge, optical diagnostic is always a good strategy because it's a non-intrusive diagnostic. And in this way, the tomographic technique has been applied to plasma diagnostic with the aim of reconstructing the plasma structure. But at this point, we have often to choose between spatial resolution and spectral resolution. And to solve this problem, spectrotomography is a very good strategy because this method can provide 2D maps of light intensities at different wavelengths, and with that, we can have access to plasma parameters such as the electronic density and temperature. Here I present the Mistral device, the machine where the measurements were performed. In this case, we are generating an argon plasma in this primary source, and after it's magnetically confined in this column. There are so many elements we can pay attention, but we are going to fix 3 important parameters. The Langmuir probes, which allow us to have a permanent control of the plasma. This spectrometer called JAS placed at the end of the column that allow us to have a radial profile in every moment of the plasma, and also the tomography plane I will explain in the next slide. Here you can see a transversal cut of this experiment. Here you can see the 2 windows and the 2 sets of optical fibers that collect all the plasma emission. These 2 fans of optical fibers and send it to a spectrometer, and after they will be computed. And here you can see a picture of the real experiment, the primary source, the plasma column, and the 2 sets of optical fibers. After computing, we have access to this kind of images. Square 2D maps with 7 pixels in each side and with a spatial resolution of about 1 centimeter. And as you can see, we have access to different wavelengths, always in the visible range. To validate our technique, we have compared the values obtained in this central row with the radial profile obtained via the JAS spectrometer. In this case, we are working always with argon plasma. And as you can see, with this spectrotomography technique, we are able to reproduce the profile of the plasma. So our technique is successfully validated. Among all the theoretical models, we have chosen the coronal model that brief say that the population of an excited state results from the balance of electron impact excitation from the ground state at the case by spontaneous emission. So we have checked that our plasma fits in this model. So we have performed measurements from the first excited state at different wavelength emissions, where the relationship between the intensity and the electronic density is linear, and also for the second excited state, where the relationship is quadratic. So we check that our plasma fits very well this coronal model, and among all the wavelength emission, we have chosen these 2 ones. for the first excited state, 751 nanometers, and for the second excited state, 454 nanometers. In this case, because this line fits this presumption, is directly excited from the ground state, and in the other case, it fits very well, and of course, the signal-to-noise ratio is very good for both of them. So, what was the method to determine the electronic temperature? So, our starting point are the two relationships of the corona model, and with these two relationships, we have arrived to an expression that is independent on the electronic density first, and also depending on an intensity ratio. With these two expressions, we are able to arrive to a fit that brings together this intensity ratio and the electronic temperature of our plasma. Of course, to be sure that this fit is accurate, we have all validated, all calibrated with the LAMU probe and the JAS spectrometer. So, with our fit, our relationship, that is also expressed here, we can have this 2D map of the intensity ratio of our second excited state and the square of the first excited state to have this kind of light intensity maps. And with the value of each pixel and this relationship, we are able to reproduce to determine the electronic temperature in each pixel with a spatial resolution of about 1 centimeter. Of course, to be sure that our measurements were accurate, we have compared the values of the central row with the values obtained via the LAMU probe. And as we can see, the two sets of measurements are in very good agreement with a maximum difference of 7%. So our measurements are good and accurate. To determine the electronic density, we have followed the same strategy. Starting from the corona model expression, we try to arrive to an expression that brings together the intensity ratios, the electronic density, but in this case, we were not able to find an expression and independent of the electronic temperature. But it was possible to arrive to this fit that brings together all the parameters needed. But of course, we have to take into account the previously found electronic temperature values. If we repeat them in proceeding with this fit and the intensity ratio map, we can determine the electronic density in each pixel of this in each pixel of our 2D map. I haven't mentioned before, but the gray pixels are physically value. These gray pixels are not logic value. So we were aware that this kind of measurements was quite indirect because we have the intensity ratio depending on the values of the electronic temperature. So we make ourselves the question if we cannot find another simpler way to determine the electronic density. So finally, we arrived that the initial expression of the corona model makes most of our requirements. We have the electronic density, we have also a function of the temperature, and we have, in this case, the intensity of only one single line. But in comparison, it's much easier. So we repeat our process. Here we have the fit needed for the determination, and we found that we were able to find also values for the electronic density in almost all the pixels. So we compare again our values with the LAMU probe once, and we found several keys. For example, the two tomographic methods are in very good agreement. It's true that this first method is quite indirect, so we can expect a lower accuracy. But on the other hand, the alternative method can provide better values, centrally if we want to appreciate the decreasing trend of the electronic density. However, the two set of measurements, tomographic measurements, are always lower than the values obtained by the Langmuir probe. But that we can explain saying that the Langmuir probe is strongly perturbative for the plasma. Sure, if we are at the center of the plasma. So this can explain this difference into the values. So finally, I would like to write the conclusions. We developed a non-intrusive tomographic diagnostic able to reconstruct the spatial profile of the plasma in 2D and spectrally resolve. We checked that the tomographic diagnostic reproduces the radial profile of the plasma. We established a method to measure the electronic temperature and density based on the intensity ratios of wavelengths that match the hypothesis of the coronal model. We have obtained a 2D electronic temperature map with a spatial resolution of 1 centimeter, and the obtained values are in very good agreement with the values obtained with the Langmuir probe, and we have measured the electronic density within two methods, and the values of these methods are in good agreement between them and also with the Langmuir probe. So thank you all for your attention, and I would like to thank again the founders of this research, the PIM laboratory and the Universidad Complutense de Madrid, which is my actual institution. Thank you. Thank you.